So we are starting with this video the topics of thermochemistry and thermodynamics. It's really just one long topic that's probably best described as thermodynamics. But in the Brown-LeMay textbook, we have it as two separate sections, and that's very common. Chapter 5 for thermochem, and then to get to thermodynamics, we're jumping a huge amount ahead to chapter 19, which those of you who are really good at math know that that means we're skipping chapters 6 through 18 for now. And that means there's a lot of information that we're kind of glossing over so that we can get to thermodynamics. And the way this is going to work is there'll be certain things that we'll just use our basic first-year chemistry understanding of in order to understand thermodynamics. And there's other things that we will have to come back to later. But the reason we do this is this will help give us a much deeper understanding of a lot of topics as we go through them. It's going to help us to understand equilibrium a lot better. It's going to help us to understand bonding a lot better. It's going to help us to understand and apply electrochem. So by doing this first, we have a foundation that will help to explain many things coming up. We start our trip into the world of thermo by looking at what I call the first rule of Chem Club here, because it's so foundational to understanding what is going on, is thinking about what kind of the central focus of what's going on in almost every chemical reaction. We're breaking some bonds and we're forming some bonds. And since we're talking about heat and energy as we look at thermo, we want to see how are those related to that foundational or fundamental process. So breaking bonds requires energy, forming bonds releases energy, and notice here and then down here, it's not until kind of the third time that I mention it that I even use the word make. Most of the times you think about we break some bonds, we make some bonds, but the word make implies that there's effort involved, that if you're going to go make a cake, it doesn't just happen on its own. But if you're trying to grab a plate out of the cupboard and you drop it, it breaks itself on its own. Kind of the exact opposite of what we're thinking about here, because in those instances, it's work in, or there's gravitational potential energy causing something to happen. We are thinking about what wants to happen here. Breaking bonds is not the favorable process. We have to put energy in. Bonds forming is favorable. We are allowing things that aren't together but want to be together to come together. So I'll go a little bit more in depth with each of these, and then we'll go on to some other key terms. But breaking bonds or breaking attractive forces, so intermolecular forces, this will be fundamental as we talk about states of matter, is endothermic, hopefully a term you know means requires energy or energy in, because what we're doing is we're taking a molecule or a compound that is connected, that is stable because of that connection, and we're forcing it apart. We're taking those shared electrons and we're making them unshared. So we don't have our complete octets. We don't have that attraction between the positives and the negatives that is allowing it to be more stable or lower potential energy. With making a bond, once again, that is the term you normally hear. A phrase I like a little bit better is allowing a bond to be made is exothermic, because we're taking those separate things that are unstable, the incomplete octets, the charged atoms, or charged ions that are separate, and allowing them to come together. We take those unstable things and they attract each other and they go into a more stable or lower potential energy position. Remembering this requires energy and releases energy is going to help on tons of explanations in the free response. It's going to help you know how to use the equations. It's going to help you know what's positive and what's negative, and it's going to get you really easy points on multiple choice. And to help visualize this, or to help you remember this, what I like to do a lot of times is just think of magnets. When we are breaking a bond, that's the equivalent of pulling magnets apart. So I'm going to do a really crude drawing here that will not in any way further your understanding, but we've got a positive and a negative. If those two things are already together and we have to force them apart, we have to pull on them. That requires energy. But when we have those two things and they are already apart, then, so the opposite of this, dual may erasing, erasing, erasing. If we had those two things, are oppositely charged things that are separate, we don't have to do anything. They are going to attract each other on their own. And then when they come together, you're going to hear a nice little click, a release of energy. That's what we're talking about here. Charged particles, either atoms, ions, protons, neutrons, well, not neutrons, but the protons and the electrons in those atoms being attracted. So taking things that are apart and want to be together, when they come together, we have a release. When things are together and we have to push them apart, that's when you're pulling magnets apart. That takes energy going in. So in every single process, I said that this idea is kind of fundamental to chemistry. So in every single chemical reaction, we are going to break some bonds or some IMFs. Our reactants have to be separated from one another. Then after they're separated, we're going to put them back together in a new way. That's going to make products. So every reaction will have steps that first require some energy and then release some energy. And if our overall reaction is endo or exothermic, depends on which of those two things used more energy. Was the breaking of the bonds kind of the larger energy step, or was the energy released when the bonds were made, was that more energy that came in? So overall, which one's greater? And as we start talking about enthalpy and we start getting into the different equations, we'll continue to see that. We'll talk about it mathematically. We'll also see it graphically. And then here, right below this, we have key terms. So I don't know, I spent 5, 6, 7 minutes here talking about this, but we've got tons of terms to learn right here, but I'm not going to take time reading them to you. You can read. These are terms you're familiar with, but you need to know in more detail. Most of them will come up in many, many later videos, but you need to know the background definitions. Me reading along isn't going to help, and I don't really have much to add to any of these because the idea is just hear the term and be ready to use it as we go on. So we got a really short video here to start, but you need to take the time to read each of these definitions, to kind of think about the symbols, to think about what you already know about them, so we can go on in our next few videos and apply it. But once again, gonna zoom back up here. This idea, breaking and making bonds, is very, very important. So in the past, I've started every single lecture day with this slide, and I've still had people missing these questions. So think about it in terms of magnets, think about it in all sorts of different ways. Just don't think about it wrong. Breaking bonds is energy in, and when we allow a bond to be made, that's a new way to say it, but we allow a bond to be made, we release energy. So we'll come back to that over and over and over again, in hopes that it becomes a permanent part of your vocabulary and an automatic thing, both conceptually and mathematically.